So imagine walking into a pharmacy. You hand the pharmacist a little slip of paper.
Right, your prescription.
Exactly, a prescription you wrote for yourself. The pharmacist takes it, reads it, counts out exactly 30 pills, puts them in the bottle, and hands them to you.
They don't ask any questions.
None. They don't ask if your knee still hurts.
Yeah.
They don't check your blood pressure. They don't, look at your history to see if it interacts badly with something else.
They just execute the instruction on the paper.
Right. And for the last couple of years, that is exactly how we've treated artificial intelligence. We write a prompt, which is our prescription, and the AI fills it.
Yeah, it's a purely transactional relationship. You are the brains, and the machine is just like a pair of hands.
Which is crazy when you think about it. Welcome to this deep dive, by the way. This is part of the Data Zen AI Podcast by the Data Zen community.
Glad to be here.
So today, we're exploring a question that is basically keeping CTOs awake at night. What if AI could plan and execute tasks step by step?
Not just answer questions.
Right. What does it look like when the AI becomes the doctor instead of the pharmacist? Because, let's be honest, most of us are stuck at level 1 AI.
Oh, totally. Level 1 is basically a conversational search engine. You open a chat window, type a question, get an answer.
Yeah. And some developers, they've graduated to level 2.
Right. Level 2 is using AI inside the code editor to build things sequentially.
Yeah.
But the human is still the director.
The micromanager.
Exactly. You say, write a database function, then, okay, write a unit test, then, wait, fix that syntax error.
It's exhausting. The cognitive load is entirely on you.
Yeah, you're orchestrating the whole workflow manually. But today, we're unlocking level 3.
Agentic AI.
Yes, agentic AI. Our mission for this deep dive is to completely bypass all the theoretical jargon.
Because there's so much of it right now.
So much. We want to show you the actual wires and gears, how the Claude ecosystem works, how agent-based systems and smart orchestration are actively changing how we work.
Right. And the first step to wrapping your head around this level 3 stuff is separating the idea of raw intelligence from the idea of a system.
Yeah, when people hear Claude, they just picture a chat window in their browser.
But Claude Code, the actual agentic environment we're talking about today, is not a chatbot.
Not at all. It's a persistent coding environment. It lives directly in your machine's terminal or inside IDEs like VS Code.
And has authority.
Right. It has the programmatic authority to read your local files, edit your source code, and autonomously run terminal commands.
Without you typing them.
Yeah.
Which brings up an analogy from our sources that I just can't stop thinking about.
The Savannah analogy.
Yes. Okay, so imagine a large language model, just the raw neural network, as a brilliantly intelligent human from like 20,000 years ago.
Standing on the open savanna.
Exactly. Standing there completely alone. They have an off-the-charts IQ. They can do complex math, logic, poetry. But they're standing there naked with just a wooden spear.
They have zero infrastructure.
Right. The human might know how to build a skyscraper in theory, but they don't have a forge to make steel.
They don't have roads. They don't have a crew to manage. That naked intelligence is severely bottlenecked.
So how does that relate to Claude?
Well, the Claude ecosystem is everything we construct around that brilliant mind. It's the house, the supply chains, the heavy machinery.
An agentic system is the language model multiplied by its environment.
Exactly. So let's look at the blueprints for that infrastructure. The documentation breaks this down into 4 foundational blocks.
Memory, skills, commands, and hooks.
Right. Let's start with memory. Because anyone using AI daily knows the exhaustion of starting a new chat.
Oh my gosh, it's like a digital Groundhog Day.
Yeah, you have to spend 20 minutes explaining, we use Python 3.dev, we use FastPI, don't use raw SQL.
It makes you want to pull your hair out.
The solution in the Claude ecosystem is a single file called claudee.md.
Okay, so how does that work mechanically?
It's a standard markdown file in the root directory of your project. Whenever you start a new session, Claude Code automatically reads it.
So it silently injects it into the system prompt before I even type hello.
Exactly. The agent wakes up already knowing the rules of the house.
That is such a friction killer. But looking at the best practices in the sources, there's a huge trap here.
Oh, massive trap.
Because my instinct, and probably every PM listening, would be to take our entire 50-page company wiki and just dump it into that file.
Yeah, let's make the AI an omniscient god on day 1.
Right. Why is that a bad idea?
The engineers at Anthropic call it big prompt chaos. You see, a language model relies on an attention mechanism.
Okay.
Even if a model has a context window of 200,000 tokens, like a huge novel, its attention isn't equal across all of it.
So if I bury a critical database security rule on page 40 of a massive file,
The mathematical weights inside the model might just assign it a low priority. It just glosses over it.
it's like handing a junior dev a 500-page manual on their first day.
Right. They nod, put it on their desk, and immediately push code that breaks production because they didn't read chapter 14.
Yeah, that makes sense. So what's the golden rule for this memory file?
Ruthless curation. You only include non-obvious constraints.
Like what?
Well, you don't need to tell Claude how to write React code. It knows that. But if your company uses a soft delete pattern...
Oh, where you don't actually delete a user, you just flip an isActive flag to false.
Exactly. You put that specific architectural quirk in the Claude.mda. If you remove a sentence and the AI wouldn't make a catastrophic mistake, delete the sentence.
Keep it incredibly lean. I love that. But that introduces a new problem for me.
What's that?
What if I have a really specific complex workflow that I only do once a month, like debugging an obscure async race condition?
Right. You don't want 5 paragraphs of async rules cluttering up your main memory.
Yeah, especially if I'm just tweaking CSS today.
That tension is why the ecosystem has the second building block. Skills.
Okay, skills. What are they?
They're stored in a dedicated folder, separate from the main memory. A skill is a reusable reasoning pattern.
So it's not a script.
No, it doesn't tell the AI what action to take. It teaches the AI how to think about a specific domain.
It's like having the AI put on a specific hat.
Yes. So for your async example, you'd write a skill file that says, when looking at concurrency, always check connection pools first, then check caching modules.
And the system just knows when to use it.
The orchestration layer observes what you're doing. When it sees you tackling a concurrency bug, it dynamically loads that specific skill into the context window.
It brings the right tools to the workbench only when needed.
That's brilliant.
Which brings us to the third block, commands.
Right. If skills are how to think, commands are what to do.
They're like macros, right? Invoked with a slash.
Exactly. Like /review security. Operationally, this enforces consistency across a team.
Because you don't want 10 developers writing 10 different prompts to check for security flaws.
Yeah, one guy forgets to ask about SQL injection, another forgets input sanitization.
So the lead engineer writes the perfect, battle-tested prompt once.
Saves it as a command, and the whole team uses it. The baseline of quality is guaranteed.
Okay, memory, skills, commands. The fourth block is hooks. And this feels totally different to me.
It is. The first 3 still require the human to initiate something.
Right. I still have to hit enter. But hooks sound like taking the human out of the loop entirely.
They introduce event-driven automation, programmatic triggers that execute actions with 0 prompting.
Give me an example of a hook in action.
A post-to-use hook. You can configure it so every time the AI saves a Python file, the system automatically runs your code linter, like Flake 8, in the terminal.
It's an involuntary reflex. The AI doesn't have to remember to lint the code.
It doesn't even have to decide if it needs linting. The environment forces the action because a file was saved.
Why are hooks so necessary, though? Can't I just tell the AI to always lint?
It comes down to probability versus determinism. A language model is a probabilistic engine. It predicts the next most likely word.
So it might just forget.
Yeah. If the context window is crowded, it will probably remember, but relying on an AI's judgment for mandatory compliance is dangerous.
But a hook is deterministic.
Right. It exists outside the neural network. It executes 100% of the time, guaranteed.
Okay, so we've built the house. We have the rules in memory, the mental models and skills, the macros and commands, and the reflexes in hooks.
Let's talk about the resident of the house.
Yes, the intelligence itself. What actually makes an AI an agent instead of just a text generator?
The defining trait of an agent is the core agent loop.
The loop. Observe, reason, act.
Exactly. An agent can observe its environment, make a decision, take an action to change the environment, and then observe the results of that action.
A self-driving cycle. Let's put that under a microscope. When I tell Claude Code, fix the checkout page crash, what is it actually observing?
This system gathers context to build a snapshot of reality. It pulls your memory file, relevant skills, terminal state, and project directory structure.
It bundles all that text up and sends it to the model. That's the observe phase.
Then it moves to reason. This is where the model thinks.
And reading the documentation, there's a feature here called plan mode that feels like a total game changer for developer anxiety.
Oh, absolutely. Press Shift plus Tab in the terminal, and it does a dry run.
It exposes the internal monologue, right?
Yeah. Normally, an agent might just start executing. Plan mode halts it, It analyzes the error and outputs a proposal to you,
I'm going to read these 3 files and modify this one specific function.
which is a huge relief. Letting an autonomous AI loose in your code base is terrifying.
It's like having a contractor say, I'm going to knock down this wall before they pick up the sledgehammer.
If it's a load-bearing wall, you can stop them. You course-correct the logic before a single line of code is touched.
So you approve the plan, and it moves to the act phase.
Right. The model outputs a JSON structure saying it wants to use a tool.
And the orchestrator intercepts that JSON.
Yes. It executes the terminal command, maybe searching for a variable, and captures the output.
And that output feeds directly back into the observe phase. The loop completes.
The agent reads the result, reasons if it worked, and decides the next step.
But mechanically, what physically stops this loop?
That is the big question.
Yeah, what prevents the agent from going rogue, spinning in an infinite loop, and burning thousands of dollars in API costs?
Loop termination is a critical piece of agentic engineering. Every time the API returns a response, there's a metadata field called stop reason.
Okay, stop reason.
If the stop reason is too loose, the orchestrator knows the model wants data. It runs the tool and prompts the model again.
The loop continues.
But if the model thinks it has fulfilled your request, it outputs final text and returns a stop reason of end turn.
That's the AI raising its hand saying, I'm completely finished.
Exactly. The orchestrator sees end turn, breaks the loop, and gives you back control.
But it only outputs end turn if it believes it satisfied the success criteria.
Which brings us to the definition of done.
Now, I know that from Agile management, but here it's a literal programmatic constraint.
It's the most important part of your prompt. If you say, make the login page look better, that's vague.
Because better isn't a mathematical finish line.
Right. It might change the color, observe it, decide the font needs changing, observe it. It traps itself in an endless loop of tweaking.
Chasing a moving target. So a proper definition of done has to be binary, pass or fail.
A good prompt is, implement a password validator. You are done when the auth-test.py test suite passes with 0 failures.
Now it has a definitive finish line.
It runs the tool, observes the terminal, sees the passing tests, and confidently returns end turn.
That makes perfect sense. But let's say I write a great definition done, but the agent just struggles.
The tests keep failing.
Yeah. The sources warn against using iteration caps to solve this, like setting a hard limit of 10 loops. Why is that bad? Shouldn't a cutoff protect my wallet?
An iteration cap is a blunt instrument. It's a safety net of last resort.
Why? What's the consequence?
Think about it. The agent is in the middle of a massive refactor. It deleted the old logic and is writing the new logic.
Oh, and it hits loop 10.
And the orchestrator violently kills the process.
You're left with half a bridge. The code base is broken.
Exactly. Or, conversely, if it's a simple task that finishes in 2 loops, but the cap is 10.
The agent might hallucinate reasons to keep working just to use up the loops.
If it doesn't have a clear definition of done, yes. The only elegant way is deterministic success criteria, so it naturally reaches end turn.
Wow. Okay, so we've covered the components and the internal psychology of the loop. I want to pull back and look at the whole factory floor.
Orchestration.
Yes. Orchestration. Yeah. When a CTO says they're building an orchestration layer, what are they actually building?
It's the connective tissue, the architectural logic coordinating all these pieces. The sources use a great visualization for this, the WAT framework.
WAT workflows, agents, and tools. Break that down for us.
Imagine a high-end restaurant kitchen. The workflows are the recipes, step-by-step instructions for a dish.
Okay.
The tools are the appliances and ingredients, ovens, knives, meat.
And the agent is the chef.
Yeah, that's it. A recipe on a counter does nothing. It needs a chef to read it.
But the chef can't cook without a stove or ingredients.
Exactly. The orchestrator is the kitchen manager, ensuring the right recipe goes to the right chef with the right tools.
But in software, the AI chef needs ingredients that live outside its own brain. A language model doesn't know what's happening on the live internet today.
Right. It's trapped in its pre-training data.
So how does it get those live ingredients? I want to spend time on this because the documentation emphasizes something called the Model Context Protocol, or MCP.
You cannot overstate how important MCP is. It solves the fundamental isolation of LLMs.
Because if a model finished training in 2023, and I ask about a database I made yesterday,
it's completely blind. It will hallucinate because it has no mechanism to see your local reality.
It's like a genius locked in a windowless room.
MCP puts a window in the room and runs a fiber optic cable through it. It's a standardized way to connect to live data.
So let's walk through the mechanics. How does a text-generating AI interact with a live PostgreSQL database?
It uses a client-server architecture. Claude Code is the MCP client. Separately, you run an MCP server.
Like a small application on my machine.
Yes. And this server has the actual database drivers and credentials.
Wait, so the AI doesn't have the database password?
No. The MCP server has the password. It exposes tools to Claude. It says, I have a tool called Run, Read, and Like Query. Give me SQL, I'll give you data.
So when Claude needs to check why a user can't log in, the loop kicks in. Reason it needs to check the database.
It constructs a specific JSON payload with the SQL query and sends it to the MCP server.
The orchestrator intercepts it, hands it over.
The server unpacks the JSON, runs the SQL against the live database, formats the rows into markdown text, and sends it back.
And the orchestrator injects that fresh text straight into Claude's context window.
From the AI's perspective, it asked a question and the universe handed it the answer a millisecond later.
It's reasoning about actual live data. It's not guessing common web errors. It's looking at the live row and seeing the account is locked.
And you can deploy MCP servers for anything. GitHub MCP for pull requests, Slack MCP for channel history, Figma MCP for design colors.
It completely eradicates hallucinations for operational tasks because it's measuring live state.
Exactly. Now, when you combine that WAT framework with live MCP data, the advanced patterns are staggering.
The sources highlight a few. Let's look at multi-agent Chrome automation. Let's move away from coding and look at an operations workflow.
Perfect example.
Imagine a marketing team has a spreadsheet of 1,000 sales leads. They need to go to every website, find the contact form, and submit a custom message.
For a human, that's soul-crushing. Maybe 3 minutes per lead. For 1,000 leads, that's 50 hours of continuous labor.
And if you hand that to a single AI agent,
it still takes 50 hours. It boots a browser, navigates, fills the form, closes the browser, moves to the next. The bottleneck is sequential execution.
But because it's software, we aren't constrained by physical bodies. We can clone the chef.
Yes. The orchestrator script reads the spreadsheet and dynamically spawns 100 independent subagents simultaneously.
100 AI clones.
Each one gets a specific URL. Using an MCP tool like Playwright, each subagent boots up a hidden headless Chrome browser.
100 browsers open at the exact same time.
They visually observe the page, reason about where the form is, generate the custom text, and click Submit.
100 forms submitted in the time it takes to sip your coffee. What was 50 hours is now 3 minutes.
That is the leverage of orchestration.
Unbelievable. Let's look at another pattern. Stochastic multi-agent consensus. Stochastic is a huge buzzword right now.
It just refers to a system having a random probability distribution.
How does an orchestrator use randomness?
Well, the stochastic nature of LLMs is usually seen as a bug when you want facts, but it's a massive feature for creative problem solving.
Because of the temperature parameter.
Right. When a model generates text, it's calculating probabilities. If you turn up the temperature, it picks less obvious words.
So if I ask for a marketing strategy 5 times, I get 5 different strategies. Statistical variance.
Yes. In a consensus pattern, the orchestrator milks this variance. If you need a breakthrough idea, you don't ask one agent, you spawn 20 independent agents.
Give them all the same prompt.
Or slight persona variations. One acts like a cynical security auditor, another like a reckless startup founder.
They all go into isolated corners and generate solutions.
When they finish, the orchestrator collects all 20 outputs and runs a consensus algorithm.
Looking for the mode, the most common answer.
Yes, to find the stable path. But more importantly, it scans for the wildcards.
Ah, the outlier ideas. The ones that only appear 5% of the time due to randomness, but end up being totally brilliant.
By orchestrating 20 agents, you scan a massive search space of ideas in seconds.
It's like having a 20-person brainstorming room instantly.
And you can take the persona idea further with agent chat rooms.
Right. Instead of working in isolation, you force them into a shared environment. It sounds like a digital reality show.
Basically, the orchestrator creates a shared JSON file as the chat history. It spawns 3 agents with conflicting personas.
Like a pragmatic engineer, a user advocate, and a paranoid security expert.
Drops a problem in the chat, build a file upload feature. Then the orchestrator prompts them to take turns speaking. They literally argue in the JSON file.
So the engineer proposes a simple script.
The security expert reads the history and replies, unacceptable, there's no file validation, it's a remote code execution risk.
And the user advocate chimes in, and there's no progress bar for screen readers.
By forcing this synthetic debate, they violently challenge hidden assumptions. They carve out all the tiny edge cases a single agent would gloss over.
The final architecture that emerges is incredibly robust. That's fascinating. But I want to bring this down to earth. Let's look at everyday, practical use cases for developers today.
The automated code review system is a perfect example. Teams are doing this right now.
Walk us through the mechanical flow.
A human developer finishes a feature and opens a pull request on GitHub. That triggers a GitHub webhook.
An automated HTTP message sent to our server with the PR metadata.
Your server receives it and triggers a post-tool use hook in your Claude ecosystem. The system reacts to the environment, no human prompt needed.
It wakes up, loads the cladedrawu.md file.
Instantly aligning with your team's specific coding conventions, then the orchestrator injects the recipe, say, /deep review.
What happens next?
It uses the GitHub MCP server to fetch the live code diff. Now, if it's a huge PR touching 30 files, the orchestrator makes a crucial decision.
It doesn't force one agent to read all 30 files, right?
No, stuffing 30 files into one context window destroys the AI's attention. It will miss bugs. The orchestrator parallelizes the problem.
It spawns 30 subagents.
One hyper-focused subagent for each file. It injects specific skills, maybe one for memory leaks, one for cross-site scripting.
Each subagent reads its file, applies the mental models, notes any flaws, and sends a report back to the main orchestrator.
The orchestrator acts as the managing editor. It aggregates the 30 reports, filters duplicates, synthesizes concerns, formats it in Markdown.
And uses the GitHub MCP to post the final review directly on the pull request.
The beauty is the speed. All of that happens in about 90 seconds.
Before the senior engineer has even finished their morning coffee, the AI has already flagged that the junior dev missed a database lock.
It doesn't replace the senior engineer. It hands them a pre-audited document. A massive productivity multiplier.
Okay, let's look at an even more intimidating use case from the sources. Repo-scale refactoring on 50,000 lines of legacy code.
Touching 50K lines of legacy code is a nightmare. It's full of undocumented behavior and spaghetti logic.
And if you just tell the AI, refactor this, you'll destroy production.
Because the AI doesn't understand code the way a compiler does. It doesn't build a dynamic structural graph.
It just processes text. It's blind to the invisible architecture of how files are imported at runtime.
Exactly. So how did the developer in the source material survive this? They used defensive orchestration.
They spent 4 days generating characterization tests before touching anything. What are those?
A standard unit test checks if code is correct. A characterization test doesn't care about correctness. It just documents what the code currently does, warts and all.
So if a buggy 10-year-old function returns a string instead of a number on Tuesdays.
And the rest of the app has secretly evolved to expect that string on Tuesdays.
Oh.
If you fix the bug, the app crashes.
Ah, so the test asserts, on Tuesday, this must return a string.
You use AI to generate thousands of these, casting a massive safety net over the entire code base.
You spend 4 days building scaffolding before touching the building.
Then they modified Claude.em.md to establish strict guardrails, directories the AI was forbidden to edit.
And then they unleashed the orchestrator to make incremental changes.
Yes. The AI updates a file, the orchestrator immediately runs the massive test suite. If a single test fails, the orchestrator instantly reverts the code.
Feeds the error log back and forces the AI to try a different approach. It's a fast, slightly blind bulldozer, and you have to put up concrete barriers.
Exactly. Now, these workflows apply to content too, not just code.
Right, the prompt asks us to cover automation workflows. Let's talk about the newsletter generator.
A perfect example of chaining MCP tools together. The human just typed, "Write me an engaging newsletter about agentic AI." That's it.
The orchestrator takes over. First, the agent realizes its training data is out of date.
So it triggers an MCP server connected to Perplexity, a live AI search engine. It pulls live data on recent funding rounds.
Now, it has the content, but it reasons a text newsletter is boring. It needs an infographic.
It connects to an image generation API, like Nano Banana, but it doesn't just ask for a generic chart.
It uses file referencing to pull the company's brand guidelines, extracts the exact hex codes for their corporate blue, and passes that into the image prompt.
Yes. But the best part was the autonomous self-healing during this step.
Right. The API request failed and returned a 400 error. The endpoint URL had changed.
If this was a traditional Zapier script, the pipeline violently crashes. You get a failure email and have to fix it manually.
But an agentic system doesn't crash. It observes the 400 error, reasons the syntax changed, searches the web for the new API docs,
Reads the updated docs, dynamically rewrites its own connection payload, and generates the image on the second try, in seconds.
without the human ever knowing. It's like a construction crew that hits a boulder and figures out a detour on their own.
Then it drafts the HTML email, but pauses the workflow. It uses a Slack MCP to message the human marketing manager.
Here are 3 subject lines. Reply 1, 2, or 3 to approve.
The human replies to. The Slack MCP feeds it to the agent finalizes it, and uses the Gmail API to send the blast.
End-to-end automation.
Yeah.
Now, we need to clarify a huge point for developers listening. When people hear AI writing code, they immediately think of GitHub Copilot.
It's a huge misconception that Copilot and Claude Code are competitors. They aren't. It's a workflow pairing.
They operate at different altitudes.
Yeah.
Copilot is embedded in the IDE editor.
It's an advanced autocomplete engine. It looks at the line you're typing and suggests boilerplate in gray text. Micro-execution.
The ultimate pair programmer whispering over your shoulder. But Claude Code is in the terminal.
You don't use Claude Code to autocomplete a for loop. You use it to reason across the entire repository. Macro orchestration.
So the better together workflow is, you use Copilot to bang out the initial API boilerplate quickly.
But then you realize this new API means you have to restructure your whole authentication layer across 20 different files.
Copilot can't do that. You switch to the terminal, wake up Claude Code, and say, restructure the auth layer to support this new model.
Claude spawns subagents, reads the 20 files, plans the refactor, executes it, and runs the tests.
Then you jump back into your IDE and use Copilot to write inline unit tests for the new structure, handing off between tactical and strategic.
This handoff highlights a major benefit of agentic workflows: sub-agent verification.
Oh, this blew my mind in the research. It addresses sunk cost bias in AI models. Break down why AI gets stubborn.
Think about a primary agent that just spent an hour writing a complex billing feature. It used 150,000 tokens.
Tried different database schemas, hit dead ends, read error logs.
It accumulates a massive history of its own journey. And because the mathematical weights are influenced by everything in the context window, it develops sunk cost bias.
It gets anchored to the path it chose.
If you ask it, is there a simpler way? It analyzes its grueling effort and replies, no, this complexity is necessary. It becomes blind to its own flaws.
Which is so human. A developer who spends 3 days on a script will fight to the death to defend it. So how do we fix the AI?
We strip away the context. The orchestrator takes only the final, completed source code, no history, no error logs.
Hands it to a brand new reviewer subagent with a pristine, empty context window.
Zero emotional or computational attachment. We prompt it. Review this for edge cases and radical simplification.
And because it has fresh eyes, it spots the obvious flaw. Why did you build 50 lines of sorting logic? Use this one-line standard function.
That strict separation one agent implements with full context, a fresh agent reviews with zero context, is the secret to enterprise reliability.
That's incredible. And building pipelines like this doesn't have to bankrupt you, which brings up the cost and speed efficiency benefit, specifically the 60-30-10 rule.
Token management is critical. Every time an agent loops, it consumes tokens, and providers charge by the token.
If you use the most expensive model, like Claude 3.5 Opus, for every microtask, your bill will be astronomical.
You don't hire a PhD physicist at $500 an hour to sort your mail.
Right. So what's the 60-30-10 rule?
60% of tasks in a pipeline are simple routing, JSON formatting, or web scraping. Route those to the cheapest model, like Haiku.
30% are moderate reasoning, like summarizing logs. Send those to a mid-tier model like Sonnet.
And only the top 10% complex multi-file debugging or the main orchestrator agent are routed to the expensive Opus model.
Intelligent routing slashes your API costs by 60%. But that leads us straight into the risks and challenges.
We have to talk about the financial blast radius. Autonomous loops without safety nets are terrifying.
The sources mention a team that set up a multi-agent PR review. A developer opened a PR with 40 changed files.
The webhook fired. The orchestrator spawned 40 parallel sub-agents to review them.
But they didn't put financial limits on the agents.
One of the MCP tools returned a malformed JSON error. All 40 sub-agents received this error simultaneously.
Oh, no.
They entered the observe, reason, act loop. Reasoned they needed to retry, acted, fail again.
And because they're agentic, they kept tweaking parameters and retrying.
They got stuck in a rapid-fire parallel retry loop. They burned through $180 in API costs in minutes before anyone realized.
$180 just to review a single PR. Imagine getting that AWS billing alert at 3 a.m. How do you prevent that?
Hard possession cost gates at the orchestrator level. The script needs a limit, say a $5 maximum spend per run.
Once it hits $5.01, the orchestrator violently halts everything and pages a human on Slack.
Developers also need to use the /cost command in the terminal to monitor real-time spend.
Which brings up the next risk. Big prompt, chaos, and context bloat. We talked about Claude.md, but this applies to the conversation history too.
The model's attention within the context window is fragile. Say you have a strict rule. Never commit AWS keys.
In a short 2,000 token session, it obeys perfectly.
But after 3 hours of debugging, the context window is 150,000 tokens thick.
That 10-word instruction is buried under a mountain of noise. It's like finding a specific Post-it note in a room completely covered in them.
The attention mechanism dilutes it. The AI ignores it and tries to commit a secret key.
So how do we fight context bloat? The documentation outlines some / commands.
The most powerful is /compact. When the AI gets confused, type /compact.
The system pauses, reads the massive history.
Uses a fast model to write a dense, summarized snapshot of decisions, drops the raw history, and replaces it with the summary. Shrinks it back down to 15,000 tokens.
Clears the clutter. Or if I'm switching from database design to CSS work, I just use /clear, wipe the slate clean.
You don't want database context polluting CSS alignment logic. And if the agent hallucinates a library that doesn't exist and writes 50 lines of garbage,
my instinct is to argue with it. No, try again. Do not do that. Arguing adds more garbage to the context window. Use the /rewind command.
It just undoes the last few exchanges, erasing the mistake like it never happened. Saves tokens and prevents future confusion.
Aggressive context management is a vital new skill set.
But let's talk about the most serious risk: security and bypassing guardrails.
AI drastically compresses the time delta between writing code and deploying it. A human takes 2 weeks to build a feature, giving security time to review it.
And AI builds it in 5 minutes. So if it hardcodes a secret or uses a bad dependency, it hits production exponentially faster.
This is why we must use hooks. Giving an AI write access to a database based on a text prompt is probabilistic compliance.
Please don't drop tables. It probably won't.
Yeah.
But if it gets confused by a migration error, it might think dropping the table is the best fix.
You cannot trust an LLM with destructive capabilities based on text. You need deterministic guardrails. A pre-tool use hook.
So it intercepts the command before it fires.
It analyzes the SQL string. If it detects a drop or delete command, the hook physically halts execution, freezes the terminal, and makes a human physically type yes to approve. The safety net is outside the agent's brain.
The sources also highlight environmental attack surfaces, like the Windows WebDAV vulnerability.
An AI agent could be manipulated by malicious code it reads online into making unauthorized network requests, bypassing local prompts.
The strict recommendation is disabling WebDA for any directory the AI touches. Security is about understanding permissions.
Wow. We have mapped the entire territory today. The ecosystem, the Observe Reason Act loop, MCP, multi-agent workflows, self-healing, infinite loops.
It's a lot to take in.
So let me play the skeptical CTO to wrap this up. Do I really need all this agentic architecture? Or am I just over-engineering? Can I just write a better prompt in ChatGPT?
You have to evaluate the return on investment. If you need a one-off Python script to rename some images, skip the complex architecture.
The overhead of setting up the kitchen isn't worth it if you're just making toast.
Exactly. Don't write a class.md, don't build MCP servers, just prompt it. Commands and skills are capital investments that only pay off through repetition.
So when does orchestration mathematically add value?
When you type the same setup instructions for the 4th morning in a row, or when a task is parallelizable, like scraping 1,000 websites.
You can't prompt your way out of 50 hours of sequential clicking. You have to orchestrate parallel agents.
Another question people ask is, are we overcomplicating the developer's role? Setting up JSON hooks in local environments sounds like just as much work as manually coding.
It really does. If it takes 2 hours to configure the AI to build a login page, why didn't I just code the HTML myself?
Because you're ignoring the compounding leverage. Building an agentic system shifts you from being a builder to a manager.
If I manually code it, I get one login page.
If you build an agentic authentication workflow, you have a system that can generate it, refactor it, debug it, and apply it to an infinite number of future projects.
It's laying train tracks by hand versus managing the robotic construction crew. It takes weeks to build the crew, but then you can build a railroad across the continent while you sleep.
Your manual labor hits a ceiling, your orchestrated capabilities scale infinitely.
Well, we've covered an immense amount of ground. Thank you for joining us on this deep dive into the Claude ecosystem. Moving from level 1 prompting to level 3 orchestration is a massive psychological shift.
From typing instructions to designing intelligent environments, I want to leave everyone with a provocative thought to ponder.
Go for it.
We discussed how objective subagents can review and correct code, removing human biases and sunk costs. As these sub-agent review systems improve, at what point does the AI ecosystem become fundamentally better at managing itself than we are at managing it?
Yeah.
And what exactly is the human developer's role when the AI is simultaneously the coder, the reviewer, and the QA department?
A question that's going to become very real very fast. If you want to dive deeper into the templates, /command, and architecture diagrams we discussed, you need to read the full source article.
It's an invaluable resource with literal code snippets.
Go to https://datazen.top podcast AI22 to read the full piece. While you're there, please click the year under the article to show your support, and be sure to subscribe to the Data Zen AI podcast so you never miss a deep dive.
Thanks for having me.
Keep experimenting, keep building, and try to be the doctor, not the pharmacist. See you next time.